previous video, we saw that the external potential is the quantity that describes the system. The features and the character of a system are also contained in the many-body wave function. It seems then natural to check the character of this mapping between the external potential and the wave function. We have already seen that this mapping is a function. It is a surjective mapping, because we have excluded the obvious non-surjective case, the degenerate ground state. Now we want to investigate a bit more and see, as we sort of guess, if the mapping is also injective. That would give us a bijective function, a one-to-one correspondence between the external potential and the wave function. Let's proceed. The strategy here is to start with an assumption. Two different external potentials leading to the same ground state wave function, and make a reduction ad absurdum. Let's see where this assumption takes us, okay? So we start from two different external potentials. To be different, they have to differ by more than a simple constant. Potential 1 gives the Hamiltonian 1 that we can diagonalize and obtain eigenvalue, the ground state total energy, and eigenfunction, ground state wave function. Similarly, potential 2 gives another Hamiltonian, let's call it 2, which again we diagonalize to obtain the total energy E2 and the ground state wave function psi. Our assumption says that for two different potentials, V1 and V2, we have the same ground state wave function psi. Here I highlight them in red. The wave functions are the same. If we focus on the two Schrödinger equations and we take the difference between the two expressions, since the difference in the Hamiltonians is only the external potential, we reach the result that potentials only differ by a constant, which is a contradiction, the absurdum, because our initial assumption was that the two potentials were different. Where does the absurdum come from? Clearly, from the hypothesis that two different potentials could lead to the same wave function. This leads to a contradiction. So the mapping between the external potential and the wave function is bijective. It is a one-to-one correspondence. And since every observable uniquely comes from the wave function via the expectation value, every observable is also a unique functional of the external potential. We are then ready to make the extra step and ask, what is the relation between the external potential and the density of a system? Before conjecturing anything, let's see what we know at the moment. We have the one-to-one correspondence between external potential and wave function. And the wave function is in relation with the density. You see here that I automatically consider this mapping to be a function. We can safely rule out, in fact, non-surjective mapping. Given a wave function, we will have only one density that is obtained by usual integration of the square modules of the wave function over all but one space variables. And this means that overall, the relation between the external potential and the density is at least a surjective mapping. And the big question is it also injective and then a one-to-one correspondence? This is a very important point. If this mapping were indeed bijective, it would mean that the density uniquely describes the system, because one density profile can lead to one and only one external potential, which identifies the system. Again, the strategy to prove this is a reductio ad absurdum. We have two different potentials that corresponds to two different wave functions. And now we make the initial supposition, by absurdum, that two different potentials or wave functions lead to the same density. From the mathematical standpoint, with the first potential, we have the first Schrödinger equation that leads to the eigenvalues E1 and the eigenfunction psi1. And potential 2, for the same reasons, leads to total energy E2 and wave function psi2. The two wave functions are different, We have seen this in the first part of the theorem. Our initial supposition says that they can give the same density. Let's see where this takes us. E1, the total energy of the first system, the system described by the external potential 1, is given by the expectation value of the Hamiltonian 1 with the wave function 1. This is a definition. For the variational theorem, if I put here any other wave function, for example, the wave function 2, I obtain a bigger value for the total energy. I can now add and subtract the Hamiltonian H2 in my expectation value in such a way to split my total energy estimate in two pieces. First, I evaluate the expectation value of H2. Since I'm taking the expectation value with psi 2, this is, by definition, the total energy of system 2. And now, second piece, I take the expectation value of the difference between the two Hamiltonians. And the difference between the Hamiltonians is only the difference between the external potentials. Let's focus on this second part here. The external potential is a one-body operator. So only one of these integrals concerns the potentials. All the other integrals only concern the wave function. So we can put the density here. Let's call it density 2 for the moment, for it comes from the wave function 2. So the final result is that the total energy of the first system, the system described by the external potential 1, is smaller than the sum of the total energy of the second system plus a simple functional of the density related to the external potential energy difference. So far, so good. We have found an inequality that says that one energy is smaller than the sum of two other energies. But now, let's do the exact same reasoning, but starting from the system described by potential 2. We write total energy 2, and we do the same procedure in which we essentially change the label 1 with label 2 and vice versa. We arrive at the conclusion, like before, that E2 is smaller than the sum of E1 plus an energy functional of the external potential difference. Let's put the two inequalities together. And let's apply our initial supposition. That is that two different external potentials and two different wave functions can give the same electron density, which we call n. If we sum the two inequalities, we obtain that a number, the sum of total energies, is strictly smaller than itself, which is clearly absurd. Where does this absurd come from? It comes from our initial assumption. Two wave functions cannot lead to the same density. So this mapping is indeed bijective. There is a one-to-one correspondence between the external potential and the density. And so every observable is in principle a unique functional of the electron density. This important result constitutes the basis, the foundation of density functional theory, as proposed by Walter Kohn in his seminal paper in 1964. This ends our demonstration of the Hohenberg-Kohn theorem. However, there are a couple of caveats and consequences of the theorem we would like to stress a bit more. So do not miss the last video of this section. Goodbye.